press can't go in. So, in any case, thank you all for coming. This is a crowd worthy of Dan's reputation. You can see that the whole family is here. And the introduction of the PhD students in the oral defense is always a lot of fun. And because they stay with us, what, 10, 15 years? So, anyways, we enjoyed Dan's friendship throughout this process very much. I know his sense of humor and mine clash occasionally. That's fine. I always learn from the diversity of the students that I work with, so I greatly enjoyed Dan's friendship and really fantastic work. He was disappointed a little bit when he broke his arm just on a great Antarctica, but then he recovered the next year. That showed perseverance, so I was very pleased. Before I finish my introduction, I would like to invite Maria to say a few things about that.
Thanks a lot for the extra opportunity. Yeah, I've been working with Dan for a few years now, and I just wanted to share a little bit of my experience with you guys. So, the first time that I interacted with Dan, there was some talk of him working on an automatic whistler detector for the group, and so I thought that was pretty interesting. So I had it in my office, and I was giving him the standard spiel that I give about the magnetosphere, and this is the stuff that gets me, really excited. It's what I love to do. And at some point, I look over at Dan, and he was just bored out of his mind. So I was like, oh, well, I don't really know if I'm going to be able to work with this guy, and so we'll see. So the next time, our next interaction was Dan was putting together a proposal for a big data server for our group, and it was something that he had pretty much come up with on his own, and it was he had sent around a draft of the proposal, and I looked at it, and it needed a little bit of work. So that was our first collaboration together, and it ended up, to make a long story short, we won the award, and we got this data server that has really, in a word, revolutionized the way that we handle data in our group, the way the data comes in, the way we access it, and what we can do with it. And then from there, we went on to work on some projects that you'll see here. And as much as it pains me to say, Dan ended up with some really nice scientific results, and I'm really proud of the work that he's done.
Thanks. Brenda, Maria, thank you very much for that. I appreciate embellishing a little bit and throwing in some good things to say about me. So, the title of my talk today is Source Variation in Ground Accessibility of Magnetospheric Mid-Latitude ELF and VLF Chorus and Hiss. I'm going to start with an introduction to ELF and VLF waves in the magnetosphere, followed by 3 particular contributions of this work and conclusions. So chorus and hiss are 2 particular types of electromagnetic waves that are generated near Earth space and may be received on the ground. I'm showing here a representation of chorus and hiss on a frequency versus time plot known as a spectrogram, which shows the evolution of the frequency of these waves in time. As you can see, chorus on the top is characterized by a series of closely spaced, discrete, generally rising tones, whereas hiss appears as an incoherent noise-like signal. These waves were originally named due to, in the early days of recordings, when waves were played through an audio speaker. Although these are electromagnetic waves, they happen to lie in the frequency range of human hearing of a few kilohertz. I'll play a few brief samples of these waves so you can get a feel for how they got their names. First, chorus, which was named after its resemblance in sound to birds chirping at dawn. Bear in mind, this is a naturally occurring electromagnetic wave that has absolutely nothing to do with birds, but nonetheless has that resemblance. And hiss, in contrast, is a classic case of onomatopoeia and doesn't really sound like anything. And you can ignore the occasional pops that occur in this recording, which are caused by interference from light. And although we do very few analyses these days using audio recordings, the names have stuck and they give a a good flavor to these two types of emissions. So to first order, the Earth's magnetic field is approximately dipolar in shape, with magnetic field lines of the source shown here. The region of near-Earth space over which the Earth's magnetic field is the dominant force is known as the magnetosphere. Within the magnetosphere and a little bit below it are several important regions of plasmas, which are dissociated electrons and ions. The first of these is the ionosphere, which is a cold and dense plasma which is found in the upper regions of the Earth's neutral atmosphere. The main role that the ionosphere plays in this discussion is in its ability to attenuate waves as they travel from their source, the magnetosphere, through the ionosphere into the ground, where this attenuation occurs due to collisions of the ionospheric particles with other ionospheric particles and with the neutral particles in the Earth's atmosphere. Beyond the ionosphere is the appropriately enough named plasmasphere, which is also a cold and somewhat dense plasma, which is trapped within the Earth's magnetic field and therefore takes on a shape that is approximately field aligned. The edge of the plasmasphere, where the plasma density exhibits a steep drop in density as you go outwards in radial extent, is known as the plasma pause. A third region of plasma within the Earth's magnetosphere is a region of warm plasma, shown here, which is strongly influenced by magnetic storms originating on the sun and is therefore very variable. Now, in contrast to the ionosphere and the plasmasphere, the warm plasma region, as its name implies, has higher energies than these two plasma regions, with energies in the range of tens to hundreds of kiloelectron volts. This is a particularly important energy range when considered in the context of interactions with electromagnetic waves. Interactions between the warm plasma particles and electromagnetic waves can either result in energy being transferred from the particles into the waves, which leads to an increase in amplitude of the waves and a deceleration of the particles, or the inverse, where waves may impart some of their energy to the particles, leading to particle acceleration and wave damping. Two particular types of waves, which I'll be discussing today, are chorus and hiss, shown here, originating from the warm plasma region, where hiss is generally sourced within the plasmasphere and chorus is sourced without. Now, the fourth and final region of plasma, which I'll be discussing today, is known as the radiation belts, which is a region of much higher energy particles of 100 kiloelectron volts and greater, which occurs with two distinct bands. First, an inner radiation belt, a gap in between which there is a minimum in density, and an outer radiation belt. The radiation belts are a particularly important area of research due to how they interact with assets in space. Among those are satellites, which the high energy electrons from the radiation belts may damage due to their collision with the electronics of the satellites, and astronauts, which may incur health problems from those same particles. This all ties back into chorus and hiss by the manner in which chorus maintains the structure of the outer radiation belt, both by accelerating electrons to relativistic energies and forming the belt, and also by scattering these particles out of the belt where they may be lost to the neutral atmosphere. In addition, the slot region in between the two radiation belts is partially maintained by hiss, which removes particles from this slot region by the same method of scattering into the neutral atmosphere. So if I can become chorus-centric for a second, the current paradigm of chorus propagation is as follows. It is currently believed that there are two main methods of chorus propagation. Either propagation in a ducted mode, in which case the wave is guided by a field-aligned density irregularity known as a duct, in which case it may reach the ground and be received on ground receivers below the ionosphere. The second method is a non-ducted mode, in which case, due to the complexities of this medium and electromagnetic waves propagating within them, in general, waves will magnetospherically reflect away from the Earth and not be received on the ground. A large portion of this work aims to show that there is, in fact, a third method of propagation of chorus from its source, namely a non-ducted mode, where chorus may propagate without the aid of field-aligned irregularities, where with the proper initial conditions, chorus may be received on the ground without the aid of ducts. either via direct path, as shown here, or via one or more magnetospheric reflections. This brings me to the contributions of this work. I first developed a method of automatically detecting and distinguishing between chorus and His emissions in broadband extremely low frequency and very low frequency, or ELF VLF data. I've created the first database of spectrally categorized broadband chorus and His emissions spanning an entire solar cycle, or about 11 years. I've determined that chorus observations at mid-latitude ground stations are consistent with propagation in a non-inducted mode, and emissions may therefore originate at field lines far removed from those of the receiving station. I've determined that the ability to observe chorus at mid-latitude ground stations is strongly dependent on instantaneous plasma pulse extent as a result of its non-inductive propagation. And I finally determined that dawn His is consistent with chorus as a source, whereas dusk His is more likely sourced by terrestrial lightning. Due to time constraints today, I will only be discussing the first 4 contributions. The first item I will discuss is automated emission detection. Now, if you wanted to perform a long-term statistical study of emissions using broadband VLF data, for example, 1 year, and you wanted to sample fairly often, for example, once every 15 minutes, for a single year of data, you would need to manually scan using your eyeballs 35,000 different data records, a subset of which might be shown here. This is not only mind-numbing, but really prohibitively time-consuming. To give an additional perspective on how much data the group has, thanks in part to our increased data volume from that data server that Maria mentioned, we have approximately 70 terabytes of data representing over 50,000 station hours, which would be quite a feat to go through manually. The solution to this problem is an intelligent automated emission detector with a block diagram of the detector developed here, shown here. The input to the automated emission detector is your original broadband data. That data is then cleaned of 2 common types of noise, and events are detected in the cleaned data. These events are then characterized, where a series of 19 scalar characteristics is determined, and these characteristics are passed as input into a sequential pair of neural networks, the first of which will differentiate between emissions and unwanted noise, and the second of which, after noise has been discarded, will distinguish between chorus and His. Before the neural networks are able to operate autonomously, they must first be manually trained. Finally, the output of these neural networks is the desired event database with chorus and His emissions detected automatically in the data. The first part of this that I'll discuss is the removal of common types of interference. So there are 2 main types of interference which may appear in broadband ELF and VLF data. The first is known as spherics, short for radioatmospherics, are the result of electromagnetic pulses from terrestrial lightning. They appear as these vertical lines on the spectrogram shown here. Spherics are removed using an autoregressive model of the signal, where a given sample of the data is modeled as a linear combination of prior samples of the data. Namely, for any given spheric, such as the one shown here, the spheric is zeroed out in the data and then replaced with a linear combination of prior known good samples. Hum is the anthropogenic parasitic radiation from human power distribution systems, which for example would be 60 Hertz in its harmonics in the United States. Hum is cleaned via a technique developed within this group by Cohen et al. 2010. And I'm sorry, I forgot to mention it appears as these horizontal lines on the spectrogram. So in this slide, I'm showing that same piece of 10-second record of data before and after cleaning via these methods, where you can see after cleaning, there's significantly higher contrast for the emission in this data between 2 and 6 kilohertz, which makes it much easier to detect.